Early in 1993, a joint venture was set up between the inventor and the Analysis Centre to carry out further R&D. Worldwide interest was aroused by two published articles, one in the New Scientist, the other in Diamond International. The equipment needed for Nagy diamond film is incredibly simple. A standard box CNC machine tool fitted with an air bearing to allow the spindle to rotate at speeds up to 30,000 RPM, providing not only speed but stability. A mop, as it's called, made out of discs of a soft material bonded together with resin. Cotton has been used successfully, so has silk. This mop, which was used in demonstrations to 200 scientists and engineers in April 1993, is made from 60 layers of silk. More layers could be bonded if a wider mop is required. The edge is carefully trimmed so that the fibres are of exactly the right length. And finally, a quantity of powdered diamond. In Nagy coatings so far, synthesized diamonds have been used with a maximum grain size of 0.5 micron. The diamond powder is fed in by a device which works on the Venturi principle, like a paint spray gun. This is fitted to a tube whose mouth is positioned just above the fringe of the mop. A measured quantity is loaded and sucked down on demand. As powder in the mop fibres is used up, so it's automatically replenished. Coating is carried out tangentially at an angle of 90 degrees. The powdered diamond is blown onto the fringe of the mop using compressed gas. It can all be carried out at room temperature and no heat is generated by the process, which means that virtually any material can be coated. No lubricant is used either. The spin rate of the mop is dictated by its diameter and by the ability of the substrate to traverse the mop. Rates of 9,000 to 22,000 RPM have been used in experiments, but for mops of 200 to 300 millimeters diameter, a spin rate of between 16,000 and 18,000 RPM seems optimum. The critical factor is the distance between the fringed ends of the mop fibres and the surface being coated. At present, this has to be gauged by trial and error, with adjustments of 1 or 2 microns at a time, until it's clear that a diamond film is being formed.
Well, it's clear that there's sufficient evidence to warrant a more detailed and extensive research program. The aims of such a program are very clear. At first, we would like to establish the structure of the film, that is, to continue with our characterization techniques to establish the form of the diamond, the extent of the diamond, to establish whether there are other phases present and the existence of amorphous carbon and graphite, etc. This will be done using transmission electron microscopy, Auger, Raman, as I mentioned earlier. But as we have a machine within the university able to grow the films, then we're going to have control over the growth process. And we'll have direct feedback from the experimental observations to the growth procedure. And this will allow us to modify as necessary to maintain or to optimize the conditions to produce more continuous films which are higher proportion containing diamond. This is a very important aspect for technological reasons. The technologist wants a continuous film. He'd like to have the majority of that film to be diamond or diamond-like so that it has the properties of diamond. We're very well aware that a lot of people are very anxious to see the results of this research. It will be not only a keystone marker with regard to academic work, but it'll also be a marker for technological advance. We are under some pressure, and we are endeavoring to produce films and the characterization as quickly as possible.